Hello, this lecture will cover pages 231 through 240 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture, the final lecture, I might add, on Synchronous Logic Design, Part F, Designs 8 and 9. If you take a look on page 231, we're going to look at design number 8. Both of these are homework problems. However, design number 8, you're actually going to build in lab and demonstrate it to me. So let's take a look at it. Cash register feeder belt digital controller. The objective is you have been contracted to design a supermarket cash register feeder belt digital controller. Here are the specifications. I want you to read these specifications 2 or 3 times if you have to and put together your basic block diagram. You have to think about this, you have to read it, you have to discuss it amongst yourselves, but come up with the basic block diagram. And I tried to help you out in that I'm showing you that there's 3 states here. I'm spelling it out for you. There's 3 states. The belt motor is off, the belt motor is paused, and the belt motor is on. It's either motor on, motor paused, motor off, motor paused, or motor on. That's 3 states. You only need 3 states here, so 2 flip-flops will do the job here. So if you take a look at a block diagram after you read your design spec, you'll see basically that it looks like this, more or less. Notice we have this student specified some information up here. You may want to read it. This is one student's work. But notice he had 3 inputs here. He had ready, asynchronous inputs, ready, count 4, or sensor. And I just had on, C4, and S1. I abbreviated these, only it made it easier in the next state to present state table. But there's 3 asynchronous inputs, and here they're listed. On, off on switch, C4, when you're at count 4, and if you read through the spec, you'll know why we have to have a counter there. Tell us we're in count 4. And in sensor, and why we have a sensor. Notice we have our 2 feedback terms here. There's 2 feedback terms coming back. So that's going to lead us to a 5 variable K-map. There's going to be 5 total inputs here, 2 flip-flop inputs and 3 asynchronous inputs. If you read the spec, there is your state transition diagram. I give you the state transition diagram. Notice here's my inputs. On, off, bar. I mean, that's the total signature. If it's high, it's on. If it's low, it's off. But we're just going to call it on. Sensor and count 4. There's our 3 states. And basically, if you're in state 0, what's going to get you into state 1? Well, on has to be equal to 1, sensor 1 has to be equal to 0, and sensor 4 has to be equal to 0. Okay. What's going to keep you in state 0 when a clock comes? Motor on being 0. In other words, when on is equal to 0, you just stay here. And basically, you can represent, or you can build this state transition diagram. And I've done it for you because in this case right here, I want you to take the state transition diagram and I want you to go to the realization of the circuit. In the next example, we do that a little bit differently. But in this case right here, I want you to see that this is all the possibilities going from belt off state, and I labeled it here. It's easier. The more you can document these, the better for the client. So I wrote in belt off state. You just don't want to stay S0. This explains, this helps you out when you're discussing this to your end user, when you design it for him or her or the company. Here's state 1. It's the motor on, the belt on state, if you will. When the belt's moving or the motor's on, the belt on. And here's the belt paused. And notice the motor, the output motor on is 0 when the belt's paused. But all these arrows represents all the possibilities in the state transition diagram with the 5 variables. So then you go from here, the state transition diagram, to your current state to next state table. And this is on page 234 of your lecture notes. Notice you have your current states. This student picked QA and QB rather than Q sub 1 and Q sub 0. But here's your current state. Here's your asynchronous inputs. On, which is the ready, if you will. Depends how you defined it. Here's sensor, and here's count 4. 0, 0, 0, 0. You treat them all as, they're all inputs, so there's 5 different inputs from 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And you only have to go down to a count of 23, because everything else is don't care. You only have 1, 2, 3 states. You only have 3 states to deal with. State 0, state 1, and state 2. Everything else is don't care conditions. If you will, everything here, all these are X's. These are all don't cares the whole way down. They're all don't care conditions the whole way down. The rest of them. But you don't have to fill that in. So basically, you're in state 0, and you have these conditions. Look at your state transition diagram and tell me what the next state's going to be. And do this for this column here. You do it for this next state column. Once you have this completed, all 24 possibilities based on the current state and the input conditions, and you're getting all that from here. This tells a heck of a story. These state transition diagrams tell the story. That's why it takes so much time. I mean, you're usually getting these with 2 other engineers or 3 other engineers in a conference room while you're drinking coffee and you're writing this on a whiteboard. You're all discussing this, brainstorming, if you will. And you get this, and this is what they look like. Once you get this, it's pretty easy moving over to this. You just take your time and you go through each possibility. Now, once you complete the next state, then you can do these controlled inputs. Then you do your JQA, KQA, and your JQB and your KQB. You fill these out. Then you go to your output maps. 5 variable maps. Showed you how to do 5 variable maps, so you should know how to do this to build the circuit on these 2 flip-flops. Here's your final output. Your final output, go ahead and put the motor on. When's the motor on here? Most of the time the motor's off. But the motor's on when you're in state number 1. So you can see when you're in state 1, motor, your 1's here. 0's every place else. So that's going to define your motor on output, your final output for motor on. You can see down here you can see that truth table. Pretty easy to do. You can do a K-map for that, but I think you can see you're in state 1. That's when the motor's going to be on. Implement that logic as simply as possible. Once you design this circuit, I want you to lay it out on an 8.5 by 11 sheet of paper. Don't do it in a little corner of a sheet, because you have to lay this out, this circuit, and I'm going to rely on you to do it, but it's going to take a complete sheet of paper with pinouts, showing all your pinouts for your JK flip-flops and for any other gate you're using, because you're going to build it and you're going to troubleshoot it, and you're going to call me over and I want to see a schematic. I don't want to see a little tiny schematic. I want to see a large schematic that I can read. That's what you're going to expect from your technicians that are helping you out. You don't want them bringing you a little speck of a little tiny piece of paper you can't even read. So lay it out in 8.5 by 11 in a landscape mode, if you will, with the pinouts. We'll build it in lab, we'll troubleshoot it, and everybody gets this to work. Might take a little bit of time, but it's quite impressive. Cash register feeder belt controller. And then design number 9, if you take a look on page 235, the automatic car wash. The automatic car wash, here's my block diagram, but on page 236 I talk about the specifications. So I did the specification on the next page. So there's a specification of an automatic car wash. and I sort of outlined it. But basically, the reason I wanted to put this page first, page 235, is you all took your car into an automatic car wash before they get it cleaned. So what happens? Well, I do a picture down here. You're driving your car in this direction right here, and you pull in into the front left tire, or one of the front tires hits that sensor, that pressure sensor. So the pressure sensor is just going to provide an input. When it's 0, you're in the initial condition, and when it goes to a 1, you start the wash. So you're just waiting for that pressure sensor to go to a 1. That's the ready signal. The ready signal up here is really just come from this pressure sensor down here. When it's a 0, there's nobody in the car wash. When it goes to a 1, your car's sitting there ready to wash. Now, so that's what this says here, ready. You can't read it, but that's one of the inputs. Then you'll have a count 0, a count 2, a count 4, and a count 6. Well, what's that all about? Well, you just design a mod 8 counter. A mod 8 counter is going to have it's just going to have 8 states. And you know how to design a mod 8 counter. It's a separate count. We don't have to build this. You don't have to build this one in lab. But here's your mod 8 counter circuit down at the bottom. It's just a free running 3-bit counter. 0, 0, 0 through 1, 1, 1. And you want to decode, and you know how to decode a count of 0, and a count of 2, and a count of 4. And a count of 6. Why are we decoding when it gets to a 0, or when it gets to a count of 2, or it gets to a count of 4? Because what happens is there's a little micro switch here in this rail. This motor goes around as your car's sitting here. This motor's going around this rail. And here's a little micro switch right here that counts. This is the clock to this counter down here. Here's your micro switch, which is counting this 3-bit counter. Well, first of all, when you go to ready, you're going to see that it turns this motor on, and it's going to count 1. And when it gets to 2, then we're going to start the wash. And when it gets to 4, you're going to start a soak rinse cycle. And when it gets to 6, that's when you do the wax. So you have to have a separate little circuit here that's going to tell you how many times this nozzle has went around this track. Because you might be off, you might be in a wash, you might be in a soak or a rinse, or you might be in a wax, depending upon the count. That's why these counters are used. These single count input lines, when it's count 0, count 2, count 4, count 6, are up here going into this logic. So, note here, we're going to use state 1 for both the soak and a rinse to simplify this. So when you're in state 1, we'll use it as a rinse, and we'll use it as a pre-soak. And we're not going to include soap in the pre-soak. So basically our outputs are going to be turn the motor on, turn on the high pressure pump, and you either have the water valve opened, the soap valve opened, or the wax valve opened. So there's only 5 different possibilities. If you just think about the way you wash a car and simplify it a little bit, it'll explain why we have this mod 8 counter down here. Why we have the block diagram with the 1, 2, 3, 4, 5 inputs up here. Matter of fact, we didn't even count the 2 flip-flops here. So we're going to end up with, you'll see in a minute, with these asynchronous inputs, we have 1, the ready, 2, 3, 4, 5, 6, 7. We have 7 inputs. That would take us to a 7-variable map. You'd have to do this design with a computer. But with multisim, it's pretty doggone easy to do. So you read over the specification, and then you just come up, for me, with the state transition diagram here on page 237. That's the homework. All you have is 4 circles, so there's your 4 states. You can label these states. This state here is going to be your off state. Okay. This state here is going to be 2 states. It's going to be 1 state, but it's going to be your soak and your rinse state. This is your wash state, and this is your wax state. So you're going to draw an arrow from here to here. When ready goes to a 1, when that tire is on that pressure sensor, you're going to go down to here, and you're going to go into your pre-soak state and your rinse state, but it's going to be the pre-soak. And then when you get to a particular count as an input, well, what count? Well, count goes to 2. You're going to move down here, and this is going to be your wash state. Then when you go to count 4, and the counter's going to tell you when you're count 4, look what happens. You come back to this state because it's going to do your rinse. You're not going to have an arrow gone from wash to wax. You're not going to have an arrow gone from here to here. You're going to have an arrow gone from here to here. You're going to have an arrow gone from here to here to wash. You're going to come back here to rinse. And then when you get to state 6, guess what? You're going to come over here to wax. Then you're going to come back here. You have to complete this state transition diagram and hand it in to show every possibility in this automatic car wash. I just got you started here. Very important observation on page 238 here. Notice from the block diagram, the total number of inputs is 7. I already talked about this. This would lead to 7 columns for inputs in the present state to next state table. These 7 inputs would result in a 7-variable K-map. We don't do 7-variable K-maps. Nobody does. Therefore, we would most definitely need multi-sim or some other computer application to solve this complex design. But there's another way to design sequential circuits that use more hardware, but they work. The method I'm going to show you next would not be good if you were to design a circuit for mass production. Okay? You would use the technique I led you up to this point, but you use multi-sim to solve it. But if you had to build 1 or 2 of these, you would use this technique that I'm going to show you next. Now, I've used this technique as a digital design engineer at Texas Instruments when we were designing simulators for the F-14 fighter back in 1975. I was responsible for the I/O unit of that mini computer in that simulator, and I actually used this technique. First, let each state be represented by its own flip-flop. In this design, we would just need 4 JK flip-flops. We couldn't get away with just using 2. In this new approach, you would just use a separate flip-flop indicating each state. Every flip-flop would indicate you're in a particular state. Form the combinational inputs that will get you into that state, which I call the get terms, and form the combinational inputs that keep you in that state, called the keep terms. Also note for this design, number 9, that the ready signal can be buffered to the low-level preset of flip-flop 0 and the low-level clears of flip-flops 1, 2, and 3. This will keep you in state 1 when the ready is low. Think about that when you look at the next page. So basically, you're not responsible for this, but it's pretty easy. I just want you to know about it. This is what I was talking about up here on to stay in state 0. But there's your 4 flip-flops, 4 JK flip-flops. This would represent state 0 when you're off. This would represent state 1 when you're in either a soak-rinse cycle. This would be state 2 when you're in wash, and this would be in state 3 when you're in wax. This is very easy to explain to somebody. You know, it's a lot easier to understand, I think, than the synchronous logic design up to now, but it leads to more hardware, obviously. Look at all this. But here's your J term. This is your get terms. This is what gets you into state, or this is what gets you, or keeps you into state 0. But that's the off state. We already know. We have that set up already from the previous comment I just made. But what gets you into the soak or the rinse state? Well, these terms get you in, or these terms get you in. That's what gets you into the soak or the rinse state. Look at the state transition diagram. You'll see this. This gets you in, or this gets you in. So J goes to a 1, and on the clock transition, you go to state number 1, the soak or the rinse. What keeps you in that state? Well, these are the terms that keep you here. So you stay in a soak rinse until these terms get you into the wash state. And these terms keep you in the wash state. And then these terms down here get you into the wax state, and these terms keep you in the wax state. And then you usually don't use these outputs directly for the pumps and for the soap, for the valves, for the soap and the water and the wax, or turning on the motor. You don't use these directly. What you do, if you look on page 240, is you just buffer them. You just run them through buffer circuits like this. There's your on, or you're ready. That's the motor on, obviously. When you're in state 2, you're in high pressure pump. Every time you're in state 2, you turn on the pump, because you're either rinsing, okay, I'm sorry, when you're in state 2, you turn on the high pressure pump because you are washing the vehicle. Anytime you're in state 2. Now, here, when do you turn on the water? Anytime you're ready. Anytime you're in a ready mode, you have water. You're either rinsing, or you're washing, or you're waxing. So anytime you're turned on, you're doing the water. State 2 is when you call for the soap. State 3 is when you call for the wax. And these out here, if something happens to the circuitry out here, you don't want to affect it in your control. So we put these buffers in as isolators. They just isolate the circuit. If this goes to a 1, this goes to a 1. If this goes to a 1, this goes to a 1. But if something happens out here, it'll take out this output circuit, which is very inexpensive. It won't get to your control. So that's why we buffer. Engineers put these buffer circuits in, these buffer gates, to just isolate. We talked about that before. And that concludes the lectures on synchronous logic design.